Welcome to the Sabre RD online training course. This series of fast-paced videos will teach you the full power of the Sabre RD simulation environment. In this section, we introduce Sabre robust design and explore Sabre sensitivity analysis. How good is my design? For most designs, good is not just a measure of performance. Instead, a design must meet performance specifications under fluctuating conditions, manufacturing variability, environmental factors, and fault situations. It must stay within cost requirements without over-engineering. A circuit that operates predictably within all specified conditions is a robust design. Sabre RD provides a complete set of tools dedicated to robust design. Sensitivity analysis determines which components have the greatest impact on design performance. Monte Carlo and Pareto analyses are crucial tools for Six Sigma initiatives. They examine how statistical variations affect design performance. Worst-case analysis identifies the extreme performance corners of your design, considering all component and environmental variabilities. Fault analysis keeps your system within safe limits when components fail. The ISO 26262 Functional Safety Standard for road vehicles recommends fault analysis. Stress analysis determines which components are subject to extreme operating conditions. Experiments automate Sabre's robust design. We'll show how to create one for each of the robust design analyses. Experiments can be applied step by step, or they can be combined into a single robust design experiment. Sabre's robust design explores a design's expansive operational space by varying parameters, executing multiple simulations, gathering data, and generating reports. It slashes execution time by using multiple cores in parallel. Circuit design begins with meeting performance criteria using nominal component values. But what happens as component values change due to manufacturing variances and aging? The performance drifts outside of specification. Tightening all component tolerances may help the situation, but that can be expensive. A better approach is to determine which parameter variations most affect the output and hold them to tighter tolerances. Sabre's sensitivity analysis is the perfect tool for this. Let's learn how Sabre's sensitivity analysis works by going through an example. The circuit is an AC to DC converter using an average model for the pulse width modulator. We want to see how discrete components and voltage sources affect the value of the DC output voltage and how long it takes the output to settle upon startup. By default, the transient analysis specifies no looping. Selecting sensitivity analysis displays its settings. However, instead of using sensitivity in this manual manner, we'll create a reusable experiment to automate the process. Note there's a Sabre training video that introduces experiments. You may wish to watch it first to become familiar with setting up and executing experiments. We open the Experiments panel along the right side and click the icon to create a new experiment. We give it the identifier name Vout Sensitivity. The Experiment tab appears along with the canvas for the experiment's tasks. For reference, we start with transient analysis using nominal values. Next, we define a graph and add plot signals for the output voltage and the current through the variable load. We execute the experiment by selecting the Simulate tab, choosing Experiment from the pull-down, and pressing the green Start Analysis arrow. Selecting the plots from the Results pane shows the output voltage ramping up to 12 volts and an increased current load at 25 milliseconds. Returning to our experiment, we click on the Sensitivity button. The sensitivity loop needs a list of parameters to vary. We'll want the values of the capacitors, resistors, inductor, and voltage sources. Clicking the question mark lets us navigate the design tree and select them one by one. Here we find the capacitance parameter for C1 and add it to our list by using the right arrow. However, a more expedient method is specifying the parameter list in the Properties pane by using wildcards. A property named Perturbation is set to 0.01. This represents a 1% incremental change to the parameters between simulation runs. We change it to a 10% increment. A transient analysis with a 50 millisecond time end is the first task in the sensitivity loop. We add the first measurement and select the output signal. By default, it will measure the value at the end of the transient run, after all the output has settled. In the Properties pane, we change its name to DC value. We add a second measure to check the output settling time. Settling time is found under the Time Domain submenu. In the Properties pane, we change the X range to measure it between 0 and 10 milliseconds and change the name. We'll cut execution time by setting the loops to multi-core and the parallel runs to 4 to match the number of physical cores on our computer. The experiment is ready, and it's time to execute it. We click on the Simulation tab, select Experiment from the drop-down menu, choose our experiment, and press the green Start Analysis button. The entire set of sensitivity simulation takes a few seconds to complete. The top item in the results is the experiment report. It shows which parameter was changed for each loop of the sensitivity analysis. Notice parameters are varied 10% from nominal. This amount was determined by the perturbation setting that we looked at earlier. The second line is the plot with the nominal settings. The last line is the sensitivity report. Page 1 lists the normalized sensitivities of the DC output voltage to each of the parameters, along with an ASCII bar chart. It shows a nominal value of 11.993 volts. As we may have suspected, the reference voltage source has a sensitivity of 1. R1 and R2, which make up a divider used to sample the output, also have high sensitivities of just under 60%. The rest of the parameters have minimal effect. R2 has a negative sensitivity, meaning that an increase in its value will lower the value of the output voltage. On page 2, we see the sensitivities for the settle time. Its nominal value is just over 1 millisecond. Let's assume we want to decrease the settling time. We see that the inductor has the most impact. Let's decrease its value by 20% to see how it influences the settle time. We go back to the schematic and make the change. It's easy to rerun our experiment and check the results. First, we check the nominal value of the output voltage. It remained at 11.993 volts. Going to page 2, we see the settle time is now below 1 millisecond. Experiments gives us the confidence to explore design trade-offs. Whenever we make a change, Experiments runs through a battery of tests ensuring complete design integrity. A system sensitivity is the partial differential of the output with respect to an input at a fixed input point. Saber's sensitivity analysis uses an approximation of this definition. It perturbs an input, measures the change in the output, and normalizes the value. This technique enables sensitivity analysis using more complex output measurements such as duty cycle and settling time. We can apply it to any circuit configuration, including switched systems. It's not limited to component values. For example, it can find sensitivities for parameters such as temperature or the on resistance of a power MOSFET. Sensitivity does not account for parameter interdependencies and assumes linear perturbations about an operating point. A more thorough approach is Saber's Monte Carlo and Pareto analyses. The advantages of this powerful tandem are explained in another Saber training video. This concludes this section of the Saber RD online training course. To download a free student version of Saber RD, go to the Synopsys website. To further your understanding of this material, go through the lab exercises found at the link listed in the description of this video.